Welcome to the deep dive. You probably walk past construction sites every single day without really thinking twice about it.
Oh, yeah, for sure. You see the scaffolding, the cranes, maybe a bunch of people in hard hats,
Right, exactly. And you kind of just assume the innovation is happening right there in the physical tools they're using.
which is what most people think. But
Yeah.
really, there's this massive, completely invisible revolution taking place right behind that scaffolding.
It's wild. Okay, so imagine handing your grandmother's famous chocolate chip cookie recipe to a literal factory robot.
Oh, boy. That would be a disaster.
It would instantly freeze up because, it doesn't know what a pinch of salt is. It has no idea what bake until golden brown means.
Right, because robots don't have eyes or taste buds. They don't have that, decades of kitchen intuition.
Exactly. The robot needs a data file that says, dispense exactly 4.2 milligrams of sodium chloride at coordinates X and Y.
And apply like 350 degrees of heat for exactly 600 seconds.
Yes. And today, the massive multi-trillion-dollar construction industry is having a very harsh realization about this exact thing.
They really are.
Their cutting-edge digital blueprints are essentially just your grandmother's recipe. They're perfect for human beings, but they are utterly useless for machines.
Which is why we are witnessing a complete rewiring of how the physical world actually gets built. It's a fundamental paradigm shift happening in the data layer well before a single shovel ever hits the dirt.
Okay, let's unpack this. Because our focus for today's deep dive is this really fascinating excerpt, and it's titled The Machine Readable Model, Engineering BIM for Robotics.
That's a great piece.
It really is. And our mission today is to explore how the construction industry is shifting from these digital blueprints meant for human eyes to execution frameworks built specifically for robotic brains.
And to really understand why the shift is happening so fast, we first have to look at what the industry thought was the finish line for the last, I don't know, decade or so.
Right, the old holy grail.
Exactly. Everyone in construction tech was sprinting toward this thing called the clash-free model.
Right, so for anyone who, doesn't spend their week knee-deep in construction software, a clash-free model was basically all about collision avoidance.
Yeah, finding the physical problems before they happen in the real world.
You use this super sophisticated 3D computer program to map out the whole building. And the goal is to make sure your digital plumbing doesn't accidentally hit your digital steel beams.
Because you definitely want to guarantee that when the contractors actually show up on site, they don't stare at a concrete wall and realize a massive air conditioning duct and a load-bearing pillar are supposed to go in the exact same spot.
That sounds like a very expensive mistake to make in real life.
Oh, it's millions of dollars. So finding those clashes digitally, just on a screen, prevents massive delays. It was undeniably a huge leap forward for the industry.
For sure. They call it Building Information Modeling, or BIM. And it gave everyone this highly detailed 3D picture of the finished product.
But our source material today drops a major reality check on that entire concept.
It really does. It says point blank that a clash-free model is no longer the finish line. It's actually just the starting point for automation.
And that single sentence just completely redefines the entire trajectory of modern building.
It's a huge pivot.
Because traditional BIM was just a visualization tool. It was literally created so a human architect could show a human engineer what the building should look like.
So the underlying currency of that whole system is just human comprehension. The humans look at the screen, they nod, and they go, got it, I see what you're going for.
Right. But the source explicitly points out the fatal flaw in that dynamic when you introduce robots. It states that robotic layout systems do not understand intent.
They don't have that intuition.
Exactly. When we make blueprints for human beings, we heavily rely on the human mind to bridge the gap between the drawing and the real world.
Right, so a human worker can look at a 3D model, see a pipe ending near a wall, and naturally interpolate the rest.
Yeah, they know they need to drill a hole, route the pipe through, and connect it to whatever is on the other side. They understand the intent.
Which brings us right back to the recipe analogy. The human worker fills in those informational gaps with just, experience.
But a robotic system does not interpolate at all.
If the digital model doesn't explicitly contain the exact mathematical instructions for that specific hole in that specific wall, the machine just stops.
It hits an error state. It relies entirely on structured data. If a wall is drawn in the software as just some generic gray block without specific material properties or precise spatial coordinates,
The robot is completely blind.
totally blind. So the old clash-free model is essentially just a really pretty 3D picture. It's totally inadequate for a machine that requires a mathematical execution framework.
The machine needs what the text brilliantly calls unambiguous geometry.
Unambiguous geometry. I love that term.
Me too.
Go,
I am so fascinated by that concept because it means there's absolutely zero room for interpretation.
None whatsoever.
So if robots can't read our human intent, how exactly do we translate a massive, complex building, like a hospital or a skyscraper, into a language a machine can actually build from?
How do we turn the 3D picture into executable code?
Right, and our source text transitions from that theoretical problem to a very practical solution, looking at a case study from a company called Roots BIM LLC.
Yeah, they tackled this exact challenge head-on. They didn't just tweak an existing blueprint, they fundamentally restructured the data from the ground up.
They created a robotics-ready model, and the text gives us their exact execution framework, which is super helpful.
It really breaks it down. They made 4 highly specific engineering adjustments to bridge this gap between human visualization and machine execution.
Let's really dig into the mechanics of this, starting with the first adjustment. The text says they focused on refining geometry to meet robotic tolerance and placement logic.
Which sounds very technical, but it's crucial.
What does that actually look like in the data?
Well, in a standard model built for humans, a pipe is really just a visual cylinder. It just shows you generally where the pipe lives.
Okay.
But for a robot, refining that geometry means defining the mathematically perfect dimensions of that pipe down to the millimeter.
Wow, down to the millimeter.
Yeah. And it also requires defining the allowable deviation, which is the tolerance. A human might see a pipe that's slightly misaligned and just, shove it into place.
Right. Close enough.
Exactly. But a robot needs to know the exact mathematical threshold of acceptable variance before it registers a failure and stops working.
That makes sense. But the second part of that placement logic, that sounds even more complex.
Is.
Because it implies we aren't just telling the machine the final destination of the pipe. Are we actually, programming the swing of the robotic arm?
That is the core of the issue right there. A clash-free final state does not guarantee a clash-free installation path.
Oh, wow. I didn't even think about that.
The placement logic has to calculate the mathematical trajectory the robotic arm must take to maneuver that pipe into position.
So it doesn't accidentally smash into the scaffolding?
Or the temporary supports, or the materials that were just installed an hour earlier. You're choreographing a highly complex physical movement in 3-dimensional space.
Not just rendering a static image. That is a staggering amount of data to add to a model.
It really is a heavy lift.
But, okay, the second adjustment Roots BIM LLC made is where I actually have to throw a flag and push back a little bit.
Oh, let's hear it.
The text says they had to ensure models were anchored to real-world survey control for layout accuracy.
Yes, survey control.
Wait a minute, though. If a digital model is already built inside a computer program using perfect, unambiguous digital math, isn't it already precise?
I see where you're going with this.
Why does it need to be anchored to anything? The math on the screen is already flawless.
Yes. And that is perhaps the single most common misconception about digital design. Yes. Inside the computer, in that pristine digital void of the software, the geometry is indeed flawless. The angles are a perfect 90 degrees. The virtual floors are perfectly flat.
Right, it's digital perfection.
The problem is that a robot is not building the structure inside a computer. It's building it on a muddy, uneven, physically imperfect job site in the real world.
Ah, and the real world is definitely not a pristine digital void.
Not even close. Think about putting on a virtual reality headset in your living room.
Okay.
The digital world inside the headset is spectacular and infinite. But if you haven't carefully mapped the physical boundaries of your actual room, like the couch, the coffee table, the television...
So you're going to confidently swing your arm in the digital world and just shatter your hand on a physical wall.
Exactly. Survey control is basically the guardian boundary for a construction site.
Okay, that makes perfect sense now.
Yeah.
You have to calibrate the digital space to the physical space.
You establish these physical, real-world monuments and data points on the actual dirt of the site. Then you mathematically lock the pristine digital model to those exact physical geographic coordinates.
So it knows exactly where it is on the actual Earth.
Right. A 3D model floating in a computer is completely useless to a robotic layout system unless those digital lines are rigorously tied to the physical ground.
Because if you skip that step,
If you skip it, your robot might perfectly assemble a complex wall panel with millimeter precision, but it'll assemble it 3 feet into the neighboring property line
yikes.
because its internal map was never synced with physical reality.
So without that physical anchor, the multi-million-dollar robot is basically operating in a vacuum, totally disconnected from the mud it's parked on.
Exactly.
Okay, so step one, mathematically refine the geometry so the robot knows exactly how to move and place things. Step two, anchor that perfect digital geometry to the messy physical earth using survey control so the robot doesn't punch the metaphorical television.
Which logically forces the third adjustment, embedding construction sequencing to guide installation workflows.
Right, because we've given the machine the what and the where, now we had to give it the when.
Time is the critical fourth dimension here. Traditional models are static. They just show the finished building frozen in time.
Like a snapshot.
Right. But buildings are constructed in a highly interdependent sequence. By embedding construction sequencing into the data, Roots BIM LLC basically turned a static 3D picture into an active, chronological set of instructions.
So if you don't sequence the data, the robot might just look at the model, see a finished room, and decide to build the drywall before it installs the massive HVAC unit that needs to go behind that drywall.
Exactly. The machine needs the workflow defined just as rigidly as the physical geometry. It needs the data to say component B cannot physically be placed until component A has been installed and secured.
Because in human construction, a project manager on site just yells at someone to stop building a frame because the electricians haven't run the wire yet.
Right. Humans can adapt on the fly. In automated construction, that dependency must be hard-coded into the execution framework. What's fascinating here is how much upfront planning this forces on the engineers.
So we have refined the geometry, anchored it to the earth, and embedded the chronological sequence. We have a perfect four-dimensional data set.
We do.
But here is the catch, and this leads right into the fourth adjustment from Roots BIM LLC.
The big pivot.
If we have all this flawless machine-readable data, why are we still forcing a robot to drag these parts through the mud on a live, chaotic job site in the first place? Couldn't we just, I don't know, build it somewhere else?
And you've hit on the natural, inevitable conclusion of having perfect data. Roots BIM LLC modularized the systems for prefabrication-ready outputs.
Prefabrication.
If the robot knows exactly what to build, precisely where it goes on the earth, and the exact sequence to build it in, you don't need to do the fabrication on the site.
So you can just break the massive building design down into logical self-contained chunks or modules.
If we connect this to the bigger picture, think about the new hospital wing they might be building in your city right now.
Okay, yeah.
Imagine if, instead of shipping raw steel and pipes to the muddy site and having workers weld them together in the rain over 2 years, 80% of those surgical suites were built in a spotless, climate-controlled factory 3 states away.
Wow. So the floors are tiled, the gas lines are in the walls, the electrical is routed perfectly, all before it ever reaches the city.
The machine-readable data allows you to send those modules directly to automated manufacturing facilities. Because the geometry, the tolerances, and the placement logic are perfectly defined, a factory robot can manufacture that complex assembly flawlessly.
Then that finished module is simply shipped to the physical site.
And they just slot it in.
Like massive, highly complex Lego bricks. That's what prefabrication-ready outputs means. The digital model is no longer just a reference document for the site. It is directly feeding the manufacturing equipment offsite.
This completely re-engineers the traditional workflow. Roots BIM LLC has taken a model meant for human eyes and transformed it into a control system.
It's brilliant.
By structuring the data entirely for machines, they created what the source text calls a seamless bridge.
Let's walk the listener through that pipeline, because this is where the invisible revolution becomes incredibly visible.
It's a clear 4-step pipeline.
Right. It starts with the digital model.
Huh.
But as we now know, this is not a picture. It is a highly structured mathematical framework.
Yes. And that data flows seamlessly to the second phase, robotic layout,
where automated rovers and drones mark the site, drill the anchors, and prep the physical space based on those rigorous survey coordinates.
which then flows directly into off-site fabrication. The perfect digital modules are built in controlled factories by other machines, completely eliminating the variables of weather and human fatigue.
And finally, that leads to on-site assembly, where the prefabricated pieces arrive at the site and are slotted together with robotic precision following that embedded 4D sequencing.
It is an unbroken chain of machine-to-machine communication.
So what does this all mean? Like, why does this matter to you, listening to this deep dive right now?
Yeah.
Why should you care about the data structures hidden behind the plywood walls of a construction site?
It's a great question.
Because the environments you live your life in, your apartment building, your office, your local hospital, they're no longer going to be constructed in the traditional sense.
No, they aren't.
Moving forward, they're going to be manufactured.
Manufactured. The philosophical shift here cannot be overstated. The author of our source text makes a really definitive statement. They say, this isn't BIM as documentation. This is BIM as a control system for automation-driven construction.
A control system.
We are no longer treating a computer model of a building like a fancy digital blueprint that gets printed out on large paper and handed to a foreman. We are treating that digital model as the literal operating system for an army of robotic workers and automated factories.
The model is the steering wheel. The data is what's actually driving the physical machines.
And when you manufacture a building using a machine-readable control system, rather than manually constructing it from raw materials on a chaotic site, you fundamentally alter the economics of reality.
You eliminate an unbelievable amount of material waste.
You eliminate the cascading human errors that cause massive budget overruns and years of delays.
You completely transform the speed at which our world can be built, adapted, and improved. We are talking about erecting complex, highly sustainable structures in a fraction of the time it takes today.
But it requires a completely new level of discipline from the engineers and architects.
They really have to level up.
They can no longer rely on the contractor's intuition to fix their ambiguous drawings on the fly. They are no longer drawing pictures, they are writing physical execution code. If the code is broken, the building doesn't get built.
So to recap the core takeaway from this incredibly dense, fascinating dive into the Roots BIM LLC case study. In the age of robotics, a digital model of a building is utterly useless if it's only designed for human comprehension.
We have moved entirely past the illusion that a clash-free 3D picture is the ultimate goal. The finish line has permanently moved.
As the source text powerfully concludes, if the model isn't structured for machines, it's not ready for the future.
And looking at the seamless pipeline from a machine-readable model to robotic layout, off-site fabrication, and automated assembly, it raises a really profound question.
Oh.
Yeah, it's something you should really mull over as you look at the buildings going up in your own neighborhood.
Hear it.
If the digital model is now directly controlling the robotic rovers on the dirt, and the complex building components are moving to automated off-site prefabrication factories, what exactly does the construction worker of the future look like?
Oh, wow.
If human intent is no longer the driving force interpreting the blueprint on the site, will the hard hats of tomorrow even need to carry physical tool belts? Or will their primary tool simply be a laptop?
Are we trading hammers for keyboards on the job site? That is wild to think about.
It really forces you to rethink what physical labor looks like in a machine-readable world.
Will the master builder of the future be a data scientist rather than a bricklayer? I guess we'll find out.
Yeah.
The next time you walk down the street and you hear the jackhammers and you look at that towering maze of scaffolding, just remember, the real heavy lifting isn't happening with the steel beams anymore.
It's all in the data.
The real heavy lifting is happening in the data. Thank you so much for joining us for this deep dive. We love unpacking these hidden layers of reality with you, and we will catch you on the next one.